To understand why the architecture in this lesson was such a breakthrough, you have to know what it replaced. Before the mid-1940s, computers were fixed-program machines. The task a machine performed was built into its physical wiring. ENIAC is the standard example. To change what it did, engineers physically flipped switches and moved patch cables by hand, and that reconfiguration could take days or even weeks for a single new task. Think about what that means. There was no software in any sense we would recognize. The program was not a thing you could write, store, copy, or load. It was the arrangement of the hardware itself. A machine that added numbers was a different machine, physically, from one that sorted them. Every new problem meant rebuilding, and that is the bottleneck the stored program concept removed. In 1945, the mathematician John von Neumann proposed the idea that fixed it. It is called the stored program concept, and stated plainly, it sounds almost too simple to matter. Both the data and the instructions are stored together in the same memory unit. That is it. But follow the consequence. If the program lives in memory rather than in the wiring, then changing the program means changing the contents of memory, which is to say, loading a different set of instructions. No screwdriver, no patch cables, no rebuild. The same physical machine becomes a word processor, a calculator, or a game depending purely on what has been loaded into it. Everything you think of as software exists because of that one decision. And notice the phrase together in the same memory unit because it is doing real work in that sentence. Instructions and data are not kept in separate places. That is what makes them interchangeable, and it is very often a one-mark question. Now the components, and I want you to look carefully at the diagram, because the single most useful thing on it is a boundary. The large box is the central processing unit. Inside it are three things: the control unit, the arithmetic logic unit, and the registers. Below that box, separate from it, is memory. That line around the CPU is the thing to remember, taking the two units inside it in turn. The control unit is the manager. It does not calculate anything itself. It directs the flow of data between the CPU and everything else, and it sends the control signals that make each instruction actually happen in the right order. The arithmetic logic unit is the calculator. It performs the arithmetic, addition, subtraction, and so on, and the logical operations, which means comparing values using and, or, and not. Between them, those two cover deciding what happens and doing the sums. Which brings us to the distinction students most often get wrong, and it is worth being precise about. Registers are inside the CPU. There are only a handful of them. Each holds a single value that the processor is working with at this very instant, an address, an instruction, or a result, and they are extremely fast because they are physically part of the processor. The memory unit is outside the CPU, that is RAM, sometimes called the immediate access store. It holds the entire running program, both its instructions and its data. It is vastly larger than the registers, and it is much slower to reach because the CPU has to go out across the buses to get at it. Those are two different things in two different places, doing two different jobs. And here is why the confusion actually costs you marks. The stored program concept is a statement about the memory unit. Saying instructions and data share the same memory only means something once you understand that memory is not the processor. Next to the instruction set. A processor cannot carry out just any instruction you care to invent. Every CPU is physically built to recognize one fixed finite list of machine code operations, and that list is its instruction set. Each instruction in the set has two parts, and the syllabus expects both names. The opcode says what to do: add, subtract, load a value, store a value, jump to a different instruction. The operand says what to do it to, which is usually either a value itself or the address in memory where the value can be found. So a single machine instruction is a verb and its object, this operation, on that thing. Everything a computer does, however elaborate it looks on screen, is ultimately a long sequence of these two-part instructions, each one drawn from the fixed list the processor was built to understand. That has a consequence worth understanding rather than memorizing. It is why programs written in a high-level language must be translated before they will run. The translator's job is to convert each high-level statement into a sequence of instructions taken from that particular processor's instruction set. And because different processor designs have different instruction sets, machine code produced for one design will not run on another, not because of a licensing rule or a software setting, but because the second processor has no circuitry for those opcodes at all. They are instructions it was never built to recognize. That is why software is published for specific architectures rather than simply for computers. So why did this architecture become universal? 3 reasons. Flexibility. The same hardware performs any task, provided the instructions for it are in memory, which is the stored program idea paying off. Efficiency. A single set of buses is used to reach memory, which keeps the hardware design simpler and cheaper than having separate paths for instructions and data. And universality. Almost every modern computer you will ever meet, from a smartphone to a laptop to a server, is built on this model. It is worth appreciating that a design proposed in 1945 is still the one in your pocket. Which leads to the last part of this lesson, because not every computer looks like one. An embedded system is a computer system built into a larger device and dedicated to carrying out one specific task, rather than a general-purpose machine that runs whatever you install on it. That phrase, dedicated to one specific task within a larger device, is the definition to write down. Inside, it has the same ingredients as any other computer: a microprocessor or microcontroller, memory holding a program that does not change, inputs, very often from sensors, and outputs, very often to actuators. Look at the examples. A washing machine runs the wash program you selected, controlling the water valves, the drum motor, and the heater, using readings from a timer and a temperature sensor. A microwave times the cooking and stops the moment the door opens. Traffic lights sequence themselves and respond to vehicle and pedestrian sensors. Car engine management adjusts fuel and ignition continuously from sensor readings. Every one of those is a computer, and none of them looks like one. The advantages follow directly from being dedicated. Because the hardware only has to do one job, it can be small and cheap to mass produce, it draws very little power, and it is fast and reliable at that one task because it is doing nothing else. The disadvantages follow from exactly the same fact. It is difficult or impossible for a user to upgrade or reprogram. It is hard to troubleshoot because there is usually no screen or keyboard to diagnose it through. And a fault often means replacing the entire unit rather than repairing it, which is why a broken washing machine controller is frequently a new controller. 4 things to carry into the exam. In a von Neumann machine, instructions and data share the same memory and the same buses. The memory unit is not the registers. Registers are inside the CPU, memory is outside it. An instruction set is the complete list of machine code operations one processor can execute. It is not the program and it is not the software. And define an embedded system by what it is for: a computer dedicated to one specific function inside a larger device, rather than by calling it a small computer.